Europe in the 1870s was still anchored to horses and tradition, yet one French engineer was already operating decades ahead of the world's future automotive capital. Long before gasoline engines or mass production reshaped transportation, he quietly built a road-going steam machine so advanced it makes early Detroit engineering look almost primitive by comparison. This wasn't the product of a massive factory or government program. It came from a single workshop unafraid to test the limits of 19th century technology. History may have tried to sideline him, but his 1875 creation forces a provocative question. How did Detroit lose a race that hadn't even begun? The steam giant versus Detroit. Picture Detroit in the autumn of 1875. When we think of this city, we instinctively imagine the roar of V8 engines, the rhythmic clanking of assembly lines, and the sharp smell of gasoline. We imagine the industrial heart of the 20th century. But if you were standing on Woodward Avenue in 1875, the air didn't smell like industrial exhaust. It smelled like oats and manure. The Motor City was, at this point in history, fundamentally powered by muscle. The Detroit City Railway Company was a massive logistical operation, successfully moving nearly 3 million passengers that year alone. Yet, every single mile of that transit relied entirely on the biological limitations of the horse. The cutting edge of American transport technology wasn't the internal combustion engine. It was the steel rail, designed simply to reduce friction for animal-drawn carts. The entire system was biological, not mechanical. Certainly there were engineers tinkering with steam in the United States. If you looked hard enough, you might have stumbled across someone like Sylvester Roper. He had built a steam-powered vehicle, but to call it a car would be a generous exaggeration. It was a steam velocipede, essentially a bicycle with a boiler strapped dangerously close to the rider's knees. It was fascinating, loud, and incredibly precarious. These contraptions were fragile exhibitions intended to shock crowds at county fairs or scientific demonstrations. They were proof of a concept, but they lacked any real-world utility. In the eyes of the public and the industrial investors of the time, the Roper steam cycle was a scientific curiosity, not transportation. But if you crossed the Atlantic Ocean that same year and traveled to the cathedral city of Le Mans, France, you would find something that shattered that perception entirely. While Detroit was busy managing stables and feeding thousands of horses, a Bell founder named Amédée Bollée was firing the boiler on a machine he called l'obéissante, or the obedient. This was no fragile tricycle. This was a mechanical leviathan. Tipping the scales at 4,800 kilograms, it weighed as much as a modern heavy-duty pickup truck laden with concrete. It didn't just carry a single daring pilot. It had a cabin for 12 passengers, a driver, and a stoker. This was a touring omnibus built with the explicit purpose of conquering long distances at sustained speeds of 25 miles per hour. The history books often tell us that the automobile was born in a workshop in Germany in the 1880s or on a frantic assembly line in Michigan in the early 1900s. That timeline is misleading. By 1875, decades before Henry Ford revolutionized the assembly line, Amédée Bollée had not only conceptualized the modern automobile, but had engineered a high-speed, heavy-lift vehicle that was already terrorizing the French police. The automobile history didn't start small. It started as a giant. Bells, capital, and cast iron. We often romanticize the image of the struggling inventor. We like to imagine a genius working alone in a cold shed, scraping together pennies to buy a single gear, fueled only by passion and perhaps a little bit of madness. That is the story we want to hear, but it is not the story of how the automobile was actually professionalized. Amédée Bollée was not a starving artist of engineering. He was the scion of a wealthy industrial dynasty, and that financial reality is the specific reason he succeeded where others failed. Bollée was the head of a bell foundry in Le Mans, a business established by his father decades earlier. This background is critical because casting bells is not simply a matter of pouring hot metal into a hole. It is high-stakes metallurgy. To create a church bell that weighs several tons and rings a perfect sustained note, you must master the science of thermal expansion, the behavior of alloys under extreme heat, and the structural integrity of massive heavy objects. When Bollée decided to build a steam car, he did not come to the drawing board as a novice tinker. He arrived with a master's understanding of how to build heavy, heat-resistant machines that could withstand immense physical stress. The skills required to cast a cathedral bell are remarkably transferable to the skills required to cast an engine block or a steam boiler. Furthermore, the Bollée family did not just make bells, They were a diversified industrial conglomerate before that term even existed. His brothers managed factories that produced hydraulic rams and wind turbines. This meant Amédée Bollée had access to a vast, secure stream of capital. While American inventors like Sylvester Roper were likely funding their experiments out of their own pockets, forcing them to build small, lightweight, and fragile contraptions, Bollée had the resources to absorb the massive cost of failure. He did not have to build a small prototype to prove the concept to investors. He was the investor. This financial safety net allowed him to skip the rickety experimental phase entirely. He went straight to heavy industry. He could afford to design a vehicle that weighed nearly 5 tons because he could afford the materials and the fuel to move it. He could afford to experiment with complex tubular boilers and twin-engine configurations because the family business was profitable enough to subsidize his R&D department. This is why l'Obéissante looked like a finished commercial product, while other steam vehicles looked like science fair projects. The scale of his operation transformed his home on the Avenue Bollée into the world's first true automotive proving ground. He constructed a dedicated outbuilding specifically designed to house and maintain his massive steam omnibus. Historians identify this structure as the first private automobile garage in history. He wasn't just building a car in his backyard. He was building the infrastructure of the automotive industry. This combination of deep technical knowledge and deep pockets meant that for Bollée, the automobile was never a curiosity. It was simply the next logical expansion of his industrial empire. 5 tons of steam power. To understand why l'Obéissante was such an anomaly in 1873, you first have to respect the sheer physics of the machine. When we look at early cars, we usually see flimsy wooden carriages with a small motor slapped onto the back. Bollée went the other direction. He built a machine that weighed 4,800 kilograms. To put that in perspective, that is roughly the weight of a modern Ford F-350 Super Duty, with its bed filled to the brim with wet concrete. Now, imagine trying to move that mass not on asphalt, but on the muddy, rutted cowpaths of 19th century France. The rolling resistance alone would have been a nightmare. Moving 5 tons of steel and wood required immense torque, so Bollée utilized a V-twin steam engine configuration. But he didn't just install one engine, he installed 2. This decision wasn't just about doubling the horsepower. It was a brilliant workaround for one of the most difficult mechanical problems in automotive history, known as the differential. Here is the problem. When a vehicle goes around a corner, the wheels on the outside of the turn have to travel a longer distance than the wheels on the inside. If the wheels are locked together on a solid axle, like a train or a simple cart, they are forced to spin at the same speed. On a turn, the outside wheel drags and the inside wheel skips. In a light buggy, this is annoying. In a 5-ton vehicle, the stress is catastrophic. The torque builds up in the axle until the steel shafts simply snap. In the 1870s, manufacturing a gear differential capable of handling the torque of a 800-kilogram vehicle was a metallurgical impossibility. The gears would have stripped or shattered under the load. Bollée knew this, so he engineered a solution that was arguably better. He eliminated the differential gears entirely. Instead, he mounted 2 independent V-twin steam engines side by side. The left engine drove the left rear wheel via a massive chain, and the right engine drove the right rear wheel. This was brute force elegance. By decoupling the rear wheels and giving each one its own power source, Bollée solved the cornering problem. The vehicle naturally allowed the wheels to spin at different speeds based on the resistance they encountered, or the driver could throttle the engines independently to assist in the turn. It was a twin-engine, chain-drive solution that bypassed the era's metallurgical limitations through clever architecture. This layout gave the machine capabilities that were unheard of for the time. L'Obéissante could climb a 12% grade, a slope that would defeat many early gasoline cars 30 years later. It didn't just climb, it hauled. The vehicle was designed to carry a driver, a stoker to shovel the coal, and 12 passengers in relative comfort. It wasn't a horseless carriage trying to replace a buggy. It was a steam-powered bus trying to replace the stagecoach system. While Americans were building toys, Bollée had built a heavy-lift transport capable of cruising at 25 miles per hour. The geometry of heavy steering. Speed is relatively easy to achieve. Control is infinitely harder. If you build a 5-ton machine that can do 25 miles per hour, you have an obligation to ensure it doesn't shake itself to pieces or careen off the road at the first curve. In 1873, the roads were not smooth ribbons of asphalt. They were rutted dirt tracks and uneven cobblestones that would punish any vehicle. If Lobesante had used a simple solid front axle, like a farm wagon, a single pothole hit at speed would have sent a violent shockwave through the entire chassis, risking damage to the delicate steam plumbing and likely injuring the passengers. Amédée Bollée recognized that speed required isolation. His solution was decades ahead of its time: independent front suspension. He implemented a design known as sliding pillar suspension. Instead of the front wheels being connected by a single rigid beam, each wheel was mounted on its own vertical pillar that could slide up and down against a spring. This meant that when the left wheel hit a rut, it moved upward independently, absorbing the shock without affecting the right wheel or tilting the main body of the vehicle. This wasn't just about comfort, it was about mechanical survival. By isolating the chassis from the violence of the road surface, the IFS protected the boiler and piping from metal fatigue, making long-distance travel mechanically feasible. But suspension was only half the battle. The other half was steering. Have you ever watched a heavy wagon make a sharp turn? The front wheels often drag sideways, scrubbing against the ground. This is because in a turn, the inside wheel needs to travel a smaller circle than the outside wheel. If both wheels turn at the exact same angle, they fight each other. On a 5-ton vehicle, this tire scrubbing would tear the rubber tires right off the rims and make steering physically impossible for the driver. Bollée solved this with advanced mathematics. He implemented what is known as Ackermann's steering geometry. It's a geometric arrangement that ensures that when a vehicle turns, the inside wheel turns at a sharper angle than the outside wheel. This geometry allows all 4 wheels to trace a path around a single, common center point. Bollée achieved this using a complex system of cams in the steering linkage. The result was a 800-kilogram behemoth that didn't just drive in a straight line, it tracked correctly through corners. It could navigate city streets without destroying its own wheels. It was a machine that was not just powerful, but controllable. 75 tickets in Paris. Before the wheels of Lobesante could even turn on the open road, Amédée Bollée had to win a battle that every modern driver understands: the battle against the Department of Motor Vehicles. Only in 1875, the DMV did not exist. There were no forms, no licenses, and no traffic laws for a vehicle that moved without a horse. Bollée spent 2 years fighting administrative gridlock, petitioning the prefect of the Sarthe department just for the right to exist on the public highway. Finally, in August 1875, he received a letter from the Minister of Public Works, Eugene Caillot. This document authorized his locomobile to travel between cities. Historians view this letter as arguably the world's first driver's license. With the paperwork in hand, the real test began on October 9, 1875. Bollée, his crew, and his passengers set off from Le Mans with a destination of Paris. This was a distance of 230 kilometers. For a prototype machine in the 19th century, this was a moonshot. It was an endurance test of seals, valves, and chains. The journey took 18 hours. That might sound slow to us, but in the context of 1875, it was a revelation. That time included stops for meals and, crucially, stops to replenish the massive water tanks required to keep the boiler steaming. The most shocking part of the trip was what didn't happen. The boiler didn't explode, the chains didn't snap, the suspension didn't collapse. The machine simply worked. When Lobesante finally rolled into Paris, the reaction was split perfectly between awe and terror. The public treated it as a sensation, crowding the streets to see the mechanical giant. The Paris constabulary, however, panicked. As Bollée navigated the boulevards, the police began writing tickets. They didn't stop at one. By the time he parked, Bollée had accumulated 75 summonses. The police were in a bind. They couldn't technically arrest him because he hadn't broken a law, but he hadn't followed one either, because the traffic code for automobiles didn't exist. He was a legal paradox on wheels. This is where Bollée's genius for public relations came into play. He hadn't named the vehicle the Titan or the Speed Demon. He named it Lobesante, which translates to the Obedient. This was a deliberate PR strategy intended to calm the apprehensions of the police and the public. He wanted to project the image of a machine that was submissive and safe, not a wild, fire-breathing locomotive. To prove it, he invited the prefect of police to climb aboard for a demonstration ride. The prefect was expecting a violent, noisy, bone-shaking experience. Instead, he found the ride to be shockingly silent and the braking to be precise. The demonstration worked. The prefect was so impressed that he ordered all 75 tickets to be canceled on the spot. He formally granted Bollée the right to circulate in Paris, provided he stayed under 16 kilometers per hour. In that moment, the automobile graduated from an unauthorized contraption to a legally recognized mode of transportation. The first series production run. Most inventors fall in love with their monsters. They spend years building a massive, complex prototype like l'Obéissante, and then they spend the rest of their lives tinkering with it, trying to keep it running, treating it like a museum piece rather than a product. Amédée Bollée was different. He looked at his 800-kilogram masterpiece, acknowledged that it was a technical triumph, and then immediately recognized that it was a commercial failure. It was too big, too expensive, and too intimidating for the average wealthy buyer. He didn't want to be the captain of a landship. He wanted to be a manufacturer. So, in 1878, he executed the most difficult pivot in engineering. He simplified. He went back to the drawing board and designed La Mancelle. If l'Obéissante was a bus, La Mancelle was a car. It was smaller, lighter, and designed not just to be driven, but to be sold. This specific vehicle marks the transition from the era of the inventor to the era of the industry. When historians talk about the start of the automotive industry, they usually jump straight to Benz in 1886, or the American assembly lines of the early 1900s. But the numbers tell a different story. Bollée didn't just build one La Mancelle for a car show, he built 50 of them. Let that number sink in, 50. In the context of 1878, 50 complex self-propelled steam vehicles is a staggering figure. Before this moment, a car was a singular object, a unique collection of hand-filed parts that fit only that specific machine. If a piston broke, you had to forge a new one from scratch to match the wear patterns of the cylinder. By committing to a run of 50 units, Bollée was effectively inventing the concept of series production. He had to create standard casting patterns. He had to streamline the assembly process. He had to create a supply chain. He wasn't just building 50 cars, he was building the organizational structure required to manufacture them. This was the moment the automobile stopped being a scientific experiment and became a catalog item you could actually buy. The ultimate proof of La Mancelle's success wasn't just the sales figures, it was the theft. In the world of industrial design, nobody bothers to copy a failure. You only counterfeit something if it works, and if people want it. Historians have discovered that, of the surviving examples of La Mancelle, a significant number are actually bootlegs. They were unlicensed copies built by other workshops in France and Germany. Other engineers looked at Bollée's design, realized it was the only architecture that actually functioned reliably on the road, and decided to rip off his intellectual property rather than trying to invent their own. These bootleg vehicles are the smoking gun. They proved that the design was robust enough to be replicated by third parties, and that the market demand was high enough to justify the risk of patent infringement. Decades before Detroit became the Motor City, Amédée Bollée had already created a product so desirable that the black market was trying to get a piece of the action. The blueprint of modern cars. Any student of automotive design will eventually memorize a concept known as the système Panhard. It is the academic term for the layout that defined the 20th century, where the engine is mounted at the front and the power is sent to the rear wheels via a drive shaft. Textbooks and historians almost universally credit this innovation to the French firm Panhard et Levasseur, citing their 1891 gasoline model as the origin point of the modern car architecture. This accreditation is not just a minor historical oversight. It is a fundamental error that ignores the physical reality of what Amédée Bollée built more than a decade earlier. If you examine the blueprints of La Mancelle from 1878, the so-called Panhard layout is clearly visible a full 13 years before Panhard supposedly invented it. Bollée made a deliberate engineering decision to mount the heavy steam machinery, specifically the boiler and the cylinders, at the extreme front of the chassis. He then routed the power underneath the floorboards using a drive shaft that connected to a differential on the rear axle. This is not a vague similarity. This is the exact front engine, rear drive configuration that would later underpin everything from the Ford Model T to the muscle cars of Detroit. Bollée chose this layout for the same reasons engineers choose it today. It optimized weight distribution, ensuring the front wheels had enough traction to steer, while the rear wheels had enough weight to grip the road. It also separated the noise and heat of the engine from the passenger compartment, which was pushed to the rear for maximum comfort. The industry standardized this design because it was the most logical way to build a car, but they credited the wrong man. We should correct the record. The architectural foundation of the automobile is not the Système Panhard. It is the Système Bollée. He continued to refine this driver-centric philosophy with his 1881 model, La Rapide. This vehicle was capable of speeds exceeding 60 kilometers per hour, but its true innovation was in the cockpit. Bollée grouped all the boiler controls and steering mechanisms around the driver's seat. For the first time, a steam car did not require a dedicated stoker to shovel coal. A single operator could pilot the machine. The architect of modernity? The obvious question remains. If Amédée Bollée was decades ahead of his time, why is the world not driving steam cars today? The answer lies not in the quality of his engineering, but in the brutal laws of thermodynamics. Steam engines are external combustion devices. They are inherently heavy because they require a massive boiler and, critically, a constant supply of water. You are essentially forced to haul a bathtub of liquid everywhere you travel. Gasoline, by contrast, is energy-dense and portable. You can carry a gallon of fuel in a can. You cannot easily carry a water supply infrastructure in a trunk. The final nail in the coffin for steam came years later with the invention of the electric starter. Once the internal combustion engine became safe to start without a dangerous hand crank, the complex, labor-intensive ritual of firing a boiler simply could not compete. Convenience is the ultimate market force. To view Bollée as a failure simply because steam lost the fuel war is a fundamental misunderstanding of history. His true legacy lies in the architecture rather than the boiler. The modern vehicle in your driveway relies on engineering principles he established. He pioneered the independent front suspension that absorbs road impacts and the precise steering geometry that allows for safe cornering. He also standardized the layout of placing the engine in the front to drive the wheels in the back. Bollée codified the DNA of the automobile when Detroit was still betting on horses. He may have chosen the wrong power source, but he undeniably designed the right machine.